Hello everyone and welcome to the Edinburgh International Book Festival. Welcome in particular to Stripped, our series of events all about comic books and graphic novels. My name is Helen Sedgwick. I'm going to be your chair for this evening, and it's a very great pleasure to welcome James Kakalios this evening. Thank you for the applause already. As I'm sure many of you know, James is not only a solid-state physicist, but is also the author of two books, The Physics of Superpowers and The Amazing Story of Quantum Mechanics. And as if that wasn't enough, he's also a consultant in Hollywood and has advised on films like Watchmen and The Amazing Spider-Man. Our format for this evening's event is that James is going to be giving a presentation for about 45 minutes, I think, and after that we should have time for a few questions. If by any remote possibility we run over time and don't have time for questions, please do join us in the signing tent afterwards. It's just next door. You can get all your books signed, and you can also ask any questions you like about physics or comic books or life and the universe in general. Can I take this opportunity to ask everyone to turn your mobile phones off, please, if you haven't already? You're a very, very good audience. All the phones are already off. James describes himself in his bio as a mild-mannered physics professor, I think. But I'm very hopeful that by the end of tonight we will have discovered a dark yet powerful secret identity beneath his calm scientific exterior. So please join me in welcoming James Kakalios.
Thank you very much. Thank you for the wonderful introduction. Thank you all for coming this evening. Thank you to the Edinburgh Book Festival for the invitation. It's a great honor. I've followed this festival, been interested in it in years, and I'm very honored to be here today. I want to thank you all for coming to on this beautiful evening to hear a talk about science and superheroes, nerds. I hope this talk is entertaining, and if not, at least educational. So let me begin. Let's see. Oh, turn this on. That would help. So a little background. How did a mild-mannered physics professor become associated with Spider-Man and Superman? In my day job, I'm a condensed matter experimentalist. So experimentalist means I work in a lab as opposed to doing theory. Condensed matter is a fancy way of saying solid-state physics. I've been working for over 25 years in research that spans the nano to the neuro. We've worked on putting nanoparticles of silicon as small as like several hundred atoms inside an amorphous semiconductor for solar cell or other applications. Also collaborating with other professors in neuroscience using techniques we developed to study noise in these materials and applying them to voltage fluctuations in the brain. By the way, I stress the 25 years because after 25 years in physics, they give you a pipe. And if there's one thing I've learned from reading comic books, you're not a scientist unless you have a pipe. All these years of graduate school, I turned into a prop comic. Anyway, all of this is not why I'm here today. I'm here today because back in 2001, I created a freshman seminar class at the University of Minnesota that was originally called Everything I Know About Science I Learned from Reading Comic Books, which my colleagues say explains a great deal. This is a real physics class that covers everything from Isaac Newton to the transistor, but there's not an inclined plane or pulley in sight. Rather, all the examples come from superhero comic books, and as much as possible, those cases where the superheroes get their science right. This is an example. Actually, we don't cover this comic in my class, but I showed this because I bought this comic as a kid because Superman was visiting a college campus. And as a child, I was interested in what life in college was going to be like. I probably didn't realize that once I got in, I was never getting out. Even as a kid, I knew that this part wasn't too accurate. But there are some things that you could see from this cover that turn out to be correct. Namely, all professors at all times always wear caps and gowns. And all professors are 800-year-old white men. Now, this class, this freshman seminar, I taught it in the fall of 2001. And it turned out to be very successful. And then in the spring of 2002, I realized with the first Spider-Man movie about to open, the first one directed by Sam Raimi, that this might be a good opportunity to get some science into the newspaper. So I wrote an article about how a key scene in a Spider-Man comic book featuring the death of Gwen Stacy, Spider-Man's girlfriend, in, as you all know, Amazing Spider-Man number 121, turns out to be a textbook illustration of forces in motion. They published this in the newspaper, and the university sent out a little press release saying, oh, Spider-Man's on the big screen, but if you want to know about the science of superheroes, the person asked is Jim Kakalios, teaches this freshman seminar, blah, blah, blah. The University of Minnesota has put out press releases about me before, about my work on amorphous semiconductors and electronic noise. Result? 0. You write one story about Spider-Man, however. And the press release came out on Friday. The movie had opened on Friday. By Monday, there were calls from the BBC, the London Times, CNN. The Associated Press came to my office, where I just happened to have those lecture demonstration tools on hand. That was a lucky break. You know, at this stage of my life, I've reconciled myself to the fact that I could win 3 Nobel Prizes, and I know what photo they're using in my obituary. I tell that to my colleagues. They say, win 3 Nobel Prizes? How? In a crap game? This article actually went around the nation. It actually went around the world. One of the students brought back a clipping from Turkey where I think I know what they're saying about me. And then I started showing up in places that physics professors don't usually appear. So over the week, this weekend, you're playing a board game with the family. If you're ever playing Trivial Pursuit, and you get volume 6, I'll tell you right now that if you get card 291, the science question, the answer is kryptons. The question is, what planet's gravity did science professor Jim Kakalios estimate by calculating the force needed to leap over an Earth building in a single bound? Now, I didn't even know about this. One of the graduate students at Minnesota showed me this card. So I borrowed it. I brought it down to the main head office, and I went to my department chairman, and I said, Alan, who's the most famous scientist you know? And he looked at the card, and he looked at me, and he said, Stephen Hawking. Who's not a genius? Oh, well, then it's you. But all of this led to my writing a popular science book, The Physics of Superheroes, which, as I mentioned, is available here. And the point is that the superheroes actually get their science right more often than you might think. Certainly the superpowers themselves are physically impossible. And I don't see my job as just being like Dr. No or Professor Grump saying, well, this could never happen, and this is impossible, and what's the deal with the Hulk's pants anyway? Unstable molecules. And so rather I say, let's give a suspension of disbelief. Let's grant a one-time miracle exemption from the laws of nature and say, if you were super strong, or could stretch like a rubber band, or could run at super speed like the Flash here, or Dash from the movie The Incredibles, could you run across the ocean? Or up the side of a building? Could you drag people behind you in your wake? All things that these characters are shown doing in the comic books using their superpowers, all things that are correct from a physics point of view once you make that suspension of disbelief. Here we see the Flash, a DC comic superhero who can run at super speed. And a crook is shooting at him, and the Flash is faster than a speeding bullet, so that's not a problem. But what about the innocent bystanders in the way? The Flash is not super strong, he's not invulnerable, he's not bulletproof, he's just very fast. But we see here, with a sweeping motion, the Flash plucked them, the bullets, right out of the air before they could harm him. And then here, there's an editor's note. Flash's action in stopping the bullets is similar to that of a baseball fielder who stops a hot grounder by letting his glove travel momentarily in the same direction as the ball. Well, this is correct. This is how, if you had super speed, you could stop a speeding bullet. Just 2 days ago, I picked up an object going 600 miles per hour when I poured myself some ginger ale on the airplane. It's going 600 miles per hour. I'm going 600 miles per hour. No problem. If I'm standing still and it's going 600 miles an hour, then I have a problem. So here is some correct physics as part of a superhero story. You could even get some more advanced topics. Here the Flash is trying to run at the speed of light. They say the mighty monarch of motion pours it on. They always had these great alliterative nicknames for the characters. The Flash was the Scarlet Speedster, the Crimson Comet, the Viceroy of Velocity. And we see him thinking here, it's taking me a little longer than usual to reach light velocity. I wonder if I'm tired or something that could affect my super speed. Good gosh, there's no doubt of it. I'm slowing down. I'm going slower and slower despite all my efforts. I can't go any faster because I'm getting heavier. Something's happening to me. Now, those of us who know Einstein's special theory of relativity know exactly why the Flash is getting heavier as he tries to run at the speed of light. An alien is shooting him with a gravity increasing ray. But if you take it out of context, it's a beautiful illustration of Einstein's principle. One more, I just love this example. Here, because of some silly reason, the Flash can't touch anyone without killing them. Don't ask. But he wants to stop a crook, but he doesn't want to kill him. He just wants to capture him. So what he does is he races around a pear tree, and he sets up vibrations that shake the pears off. Then, by racing swiftly back to the car, I'll start a suction to draw the pears after me. And I'll duck down, and the pears traveling at high speed will do my job for me. Thereby demonstrating Newton's third law of motion, which is usually expressed for every action there is an equal and opposite reaction, or as I like to put it, forces come in pairs. All right, I saw some faces there. I saw some groans. For those of you groaning, I just want to point out that I am a teacher. Therefore, your hatred only makes me stronger. But we could actually talk about some more advanced topics. We could talk about electricity. We'll talk about that in regarding Electro, a Spider-Man villain. Electro was up on a high tension line when he was struck by lightning, and thus obviously gained the ability to store electric charge and discharge it at will in the form of lightning bolts. You know, as a kid, I could probably be forgiven for thinking that getting hit by lightning was probably the greatest thing that could ever happen to me, second only to wallowing in radioactive waste. It's like, I'd be stupid not to do this. And by the way, personally, and you probably might have a different opinion on this, but if I gain mastery over one of the fundamental forces of nature, I don't know if these are the clothes that I'd wear in public. But this is just one in a series of bad choices that leads these guys to a life of crime. And so here in the story, Spider-Man's fighting Electro, and he's deflecting one of the lightning bolts by tossing a ball bearings in the air. And then later on he deflects another bolt by tossing a metal chair overhead, saying, anyone with any knowledge of science knows that anything metal can act as a lightning rod, as this steel chair is doing. Well, actually, Spidey, anyone with any knowledge of science knows that this is true. If the chair were grounded and there was some place for the electricity to go, it's not that electricity is attracted to metals. It's just that you hit the lightning rod so you have a shortcut path if there's a grounding cable. Otherwise, you just found a better way to set your house on fire. Water goes from the faucet to the drain because of gravity. It's not attracted to drains. It's not like if you put a drain on the ceiling, the water will go, there's a drain! And arc up. And you go, no, but gravity's out. Forget gravity, there's a drain! I'm going for it. Doesn't work that way. It gets even worse. The next time he fights Electro in Amazing Spider-Man Annual #1, he takes the effort of deliberately grounding himself, right? He says, good thing I grounded myself. I'm able to take the full effect of it thanks to the addition of my spider strength. Kids, don't do this. Promise me, if you ever fight a villain that has electric powers, don't ground yourself. Now, it's actually interesting. This was 1963 Marvel Comics. But if you go back to 1938, Action Comics #1, there seems to be a different understanding of grounding. This is Superman's very first appearance, Action Comics, June 1938. Superman wants some information from this guy, but at this point in the storyline, nobody knows who Superman is. Nobody knows that he has special powers, that there's anything special about him. So Superman wants some information from him, and seeing Superman dressed in this blue unitard with this red cape and these little red panties here, he decides to not cooperate. So Superman grabs him and jumps up and starts running along a high tension line, carrying him like a sack of potatoes. And the man panics, saying, "Stop, stop, we'll be electrocuted." "No, we won't," says Superman. "Birds sit on telephone wires and they aren't electrocuted. Not unless they touch a telephone pole and are grounded." Oops, almost touched that pole. By the way, I see that looking class a lot. A test? I leave it to you whether Superman giving this guy a physics lesson counts as an extra form of coercion or something. But Superman is exactly right. How do you take a glass of water that's filled up all the way to the brim, no lid, no cap, no ice on the top? How do you take that glass, turn it upside down, and keep all the water in the glass? Do it underwater. No place for the water to go, stays in the cup. Right? If I'm at 10,000 volts and everyone else is at 10,000 volts, I don't have a problem. If I'm at 10,000 volts and you're at 0 volts, then I got a problem. It's the voltage difference that pushes the current that would be lethal. So here we get some accurate science, again, back in very first Superman comic. Anyone know, by the way, little trivia question, who this guy is? It's not Lex Luthor. The very first person Superman roughs up in his very first adventure is Bob Gear, the slickest lobbyist in Washington. It's June 1938, where America's in the depths of the economic depression. The very first people Superman goes after are crooked politicians, sweatshop owners, slum landlords, people who run unsafe coal mines. It's only when he's the top of a multi-million-dollar marketing enterprise that he starts going after, like, Brainiac, Metallo, people who want to take over the world but will leave the U.S. corporate power structure safely undisturbed. But I also want to talk about the world of tomorrow. I want to talk about quantum mechanics in my other book, which also features superheroes. And because comic books were always envisioning what the world of the future was going to be like. In fact, actually, back in the 50s, Superboy had an adventure with these heroes, these superpowered characters who came back from 1,000 years in Superboy's future. And they had formed a society, the Legion of Superheroes, that they were actually just pranking Superman by keeping him out of the club. They actually came to invite him into the club. But they featured what life was going to be like in the future, and it was going to be driven by science. In the Legion of Superheroes, if there was a crime, you didn't call the police, you called the science police, because it's the future. This is actually perfect for this festival. Here in this issue, Lightning Lad has been falsely accused of a crime and is imprisoned here. And because it's the future, they have a control panel that at a press of a button will provide all of the necessities of life. And for those who can't read it, it says there's a button for food, a button for water, and a button for books. Because once you have food, water, and books, you're set. Don't let me out. But in the science fiction, the pulps back in the 30s and 40s and 50s thought that by the 21st century, which we are well into now, we'd have jetpacks or flying cars, when what we got instead were cell phones and laptop computers. Though some people are kind of reluctant to give up on the jetpacks. I love how he has his Comic-Con badge as a little tail of the kite there. But we do have jetpacks today. Why don't we take jetpacks to work? Well, you could if you live next door to where you work. Because it takes a tremendous amount of energy to lift you up off the ground. And once you've expended that energy, there's hardly anything left to get from point A to point B. In fact, the Federal Aviation Administration has just recently approved for tests a jetpack that can keep someone in the air for 7 minutes. And this is what it looks like. Because you have to carry a lot of fuel. And unless you're going to have an unlicensed nuclear power pack on your back, in which case you're a Ghostbuster, there just isn't enough energy to lift you up. The science fiction pulp writers back in the 30s thought that we'd have a revolution in energy, which is what you need in order to have jetpacks and flying cars, when what we got instead was a revolution in information. And that revolution in information was made possible thanks to semiconductor and solid-state physics, which in turn was made possible by quantum mechanics. And I actually, in researching the amazing story of quantum mechanics, I found a very interesting coincidence. And it's just nothing more than a coincidence, but I think it's kind of cool. Amazing Stories was the first science fiction the first pulp magazine devoted exclusively to science fiction. Its first issue appeared in April 1926. Also publishing in that spring of 1926, Erwin Schrödinger, publishing the Schrödinger equation, which forms the foundation of modern quantum mechanics, which led to the world that we have around us. So these two visions of the future, in essence, start at nearly the exact point in time. One leads to lasers, and the other to death rays. Schrödinger develops the Schrödinger equation, and a handful of other scientists, Heisenberg, Pauli, Born, Niels Bohr, Einstein, Max Planck, because they're trying to understand how atoms behave and how they interact with light. A generation later, scientists at Bell Labs developed the transistor, and separately another group developed the laser. You don't accidentally make a laser, right? In comic books, they're always doing this. They're taking power supplies and printed circuit boards, putting it in a box, shaking it, getting a fully functioning death ray. It's not that easy. I've tried. You have to go into the lab and willfully, with malice aforethought, go and build a laser. And you can't do this without an understanding of how atoms interact with light provided by quantum mechanics. So in the 50s, we get transistors and lasers. A generation later, we get CD players, personal computers, cell phones, DVDs, iPods, everything, my kids say, without which life is not worth living. None of these are possible without the transistor or laser, neither of which are possible without quantum mechanics. If you went to Schrödinger and you said, "Nice equation, Erwin, what's it good for?" He's not going to say, "Well, if you want to store music in a compact digital format." But without the insights provided by really these true superheroes of science, the world we live in would be profoundly different. So at this stage, I need to teach you all quantum mechanics. And I have 10 minutes, which leaves me with a problem. What do I do with the other 8? Because there's a lot of philosophy that goes and difficult concepts that go into quantum mechanics. But if you're willing to throw that all out, it's actually pretty easy. If you're willing to accept 3 impossible things, then I can tell you how lasers work. And from lasers, I can tell you how CDs and DVDs work. So the 3 impossible things are, light has both a wave and particle-like property. It acts like a little packet of energy called a photon. Of course, we know about this. We know that they're actually useful for military applications. The other idea is that matter has both a particle and wave-like properties. And one hallmark of that is to look at, say, interference. When you have a wave that comes in and strikes a surface, maybe it goes through the material and reflects off the back surface and comes in. And if the 2 waves have peak to peak and crest to crest, trial to trial, then they add up coherently, or if they're completely out of phase, they cancel and you get nothing. And this is why we see nice colors on oil slicks after a rainstorm. The oil is lifted up off the water, the wet pavement, because it's repelled by the water. So it's a finite thickness slab. The light comes in, bounces off the top surface. If the slick is not too thick, it also bounces off the back surface and comes out. And because the thickness varies, different wavelengths have different coherent interference, constructive interference, so we see this nice pattern of light. We can also send a laser beam through a grid, and we see this pattern of bright and dark spots, which is a diffraction pattern, a hallmark of interference. But if we send electrons and bounce them off the surface of the crystal, and we adjust the momentum of the electrons just right, we can see a pattern that looks just like the laser light. So these are electrons. That's a laser. Those are electrons. They have this. If you just looked at the pattern, you couldn't say whether you're looking at light or electrons. The pattern alone couldn't tell you. So it looks just like a wave. The other impossible thing, everything has an intrinsic spin, or intrinsic rotation. Well, the pulps, told us that everything spin, but kind of spinning like a ballerina. And as ballerinas can only spin either clockwise or counterclockwise, this intrinsic spin can either go in one direction or the other, at least for things like electrons and protons and neutrons. And with that spin, with that rotation is a magnetic field. And as opposed to a single magnetic charge, it's like every electron, every proton, every neutron is like a little bar magnet having to do with that rotation, that spin. Why? Shut up, that's why. At the end of the day, we don't really understand it. But it is. That's the way the world is. And then when you take some of these spins and you add them together, you can have them spin one direction or the other direction. The magnetic fields can point one way or the other. This is important because, as the Dick Tracy comic strips used to tell us, the nation that controls magnetism will control the universe. But it's also important because this property of matter, which was unknown until the 1920s and 30s, is the principle that underlies being able to see inside a person. Right? The science fiction thought that you'd have to have X-ray vision in order to see inside a person. But we now can do that routinely with our magnetic resonance imaging. And what that magnetic resonance imaging does is you're inside a large magnet, it polarizes the little magnets inside the nuclei in your atoms, and then by sending radio waves pass through your body easily, which is why you can hear the radio when you're holding it behind your back. Right? The radio waves pass through your body, and then you can measure the degree of polarization and get information about what atoms are where inside your body. So one of my colleagues at Minnesota actually demonstrated this for me, where he took some candy and he put it in his magnetic resonance imaging. Does anyone know what this is? I think this is here in Scotland. Yes, these are Reese's peanut butter cups. Very good. That's right. So without having to bite into it, because we'd hate to have to do that, you can verify that they are indeed filled with delicious peanut butter, though I'd get that spot looked at. So, how can we combine this all into how atoms interact with light? If electrons have a wave associated with their motion, what are the rules that with how these waves can be arranged? You know, if you have a guitar string, you can't set up any arbitrary wave. First of all, if you could, there wouldn't be very much point to having a musical instrument if it could sound every single pitch at the same time. This wave is possible, say, for a clamped string, but this wave is not. What if I were to take this clamped string and I bend this around so it's in a closed loop? Well, then that means that only certain wavelengths could fit inside a closed orbit. So that means that only certain energies can fit inside that closed orbit. So one of the most amazing things about quantum mechanics is the electrons in the atom can go around and orbit the nucleus, but they can only go at certain energies. They can only have certain energies. You're on a racetrack, and you're in a car, and you can go only in multiples of 10 miles per hour. So you can go 10, 20, 30. You can imagine 57 miles per hour. It's theoretically conceivable, but you can never drive that fast or that slow. You can go 50 or 60. If you want to decelerate, you can go from 60 to 50, but not 57. A huge gust of wind comes up behind you and tries to make you go faster from, like, say, 30 to 34, you ignore it. Only if the wind pushes you from 30 to 40 do you speed up. Otherwise, it's like the wind isn't there. That seems crazy. And when you're looking out the window, thinking about how crazy it is, think, why am I able to look through the window? It's because the molecules have an energy gap in the ultraviolet that we can't see. So the visible light that doesn't have enough energy passes right through. The fact that you can look through a window is quantum mechanics in action. Because and if you could see in the ultraviolet, you would see a big black square where the window is. So that alone is a manifestation of quantum mechanics. In order to have some time for questions, I am going to, oh, you know what? I got to show you this, though. I'm sorry. All right, stop saving. Though saving is good. I just got to point out, and then I'm going to jump to the lasers. If light is a photon, packet of energy, what are the rules for when an atom changes its energy by a discrete amount? Well, then that means that when it goes from one energy to the other, only certain energies or only certain wavelengths can be emitted from an atom, not all colors. And in fact, when you put an atom in, like, say, a high energy beam and excite it into many different states and it drops down, you see certain wavelengths. Here for sodium, you see a yellow line. For a neon, you see a lot of red, which is why neon signs are red. Right? These are the fingerprints of atoms. Because of the different nuclei, the different electrons, only certain transitions are allowed. Only certain transitions are possible. And this is how we discover new elements. Helium was discovered by looking at the light from the sun and seeing lines that didn't correspond to hydrogen. And they first thought, no one had ever seen this before, they first thought that this was an element that only existed in stars. So they named it after the sun god, Helios. And it wasn't until years later that terrestrial sources of helium were discovered. And up until then, in the Thanksgiving, the Macy's parade, they used to drag the deflated balloons down Broadway. It's kind of a pointless spectacle, but we could actually see this applied in comic books again. Here's from an old DC Comics science fiction comic book, and here's a scientist who's made a discovery. He's looking at a spectrogram, and he's discovered this line reveals the presence nearby of a radioactive metallic element hitherto undiscovered in the entire solar system. Right? First of all, this is right. Scientists think in complete sentences. And when we talk to ourselves, we do say hitherto, which is why we tend to work alone in the lab. And we wonder why we're not invited to more parties. But this is, in fact, you see the right type of a spectrogram showing up there. Now, I'm going to jump ahead a little bit to get to the lasers. So let's see if I can. Okay, so now we know enough quantum mechanics, actually we do, to understand the physics of lasers and the physics of DVDs. So there was actually a big competition between many different research labs to build the first laser. And while the first working laser that worked in the microwave region of the spectrum, the maser, was first developed at Bell Labs, the first working laser that worked for visible light was developed by Ted Mayman at the Hughes Research Lab. Of course, competition between research labs is old news if you read comic books, not a new phenomena. Here from an old Tales from Suspense comic back from the 1960s, we see a research lab and this one guy saying, Howard ought to work on vitamin pills. He might discover one that'll help him grow into a man. Here's the senior scientist, because he's got a pipe. careful, he's liable to hear you. Then you'll start another fight and you'll have to beat him up again. I just love that again. Like, how many fights do they have in this lab? Now, one of the things, actually, these comics were part of Marvel Comics before they put out the Fantastic Four and Spider-Man. They were putting out giant monster comics, Tales of to Astonish, Tales of Suspense. Every month, the Earth was being attacked by some sort of giant space invader. And we would be doomed. The military couldn't stop them. Local law enforcement was useless. Earth would be conquered if not for the actions of a lone scientist. And here we see at the end of this story, the sheriff saying, well, I never even thought of that. And the townsman says, that's why Evans is a scientist, and you're only a sheriff. And his wife says, oh, darling, forgive me. I've been such a fool. I'll never complain about you again. Never. I can't tell you how often I hear that in my house. Probably because it involves imaginary numbers. But it's a good thing these scientists are on the case, because if it's not Groot, we have to worry about Lokar, or Orgo, or Moomba, or Rambu, or Gruto, or Grog, or Gugam, son of Goom, or Fin Fang Foom, though all of these pale against the most horrifying monster of all, the tax collector from outer space. Now, oh yeah, thank goodness my watch stopped. Anyway, so how do I make a laser? I told you that quantum mechanics says that only certain energies are allowed. And if I bring many of these atoms together, they all have their own separate energies, but they might be, and they all will be filled with electrons, and then there will be a gap in energy, and then there will be other allowed orbits that just don't happen to have electrons in them at that time. It's a material like window glass is kind of like a large auditorium where there's an orchestra and a balcony. And if every seat in the orchestra is filled, then there's no place for anybody to go. If you try to push people and say, move on, they would ignore the push because there's no empty seats to go to. So that's why these materials like window glass do not conduct electricity, because there's no place for the current to flow. If you provide enough energy to push the electrons up into the balcony, oh, there's plenty of empty seats here. So here they can now conduct electricity. So this is also, so if you shine light on the material that corresponds to this gap, suddenly a current can flow. And this is in fact the basis behind television remote controls that use infrared light to activate the semiconductor detectors and close the circuit in a sense. So again, without quantum mechanics, we wouldn't have TV remote controls. To the men in the audience, you're welcome. So okay, I have all these states filled. These are empty. That's an insulator. That's not a laser. What if I put a mezzanine, a level just down underneath here? Initially, that level is going to be empty. There's a little row here. So what I'll do is I'll shine light on the material. Electrons pop up into the balcony, and some of them fall down into the mezzanine where they sit. The mezzanine turns out to be hard to get into, but if it's hard to get in, it's hard to get out. So if I put an electron in the mezzanine, it'll sit there for a while. Then I turn the light off, and eventually the electrons drop down from the mezzanine into the orchestra. There are empty seats in the orchestra because they were popped up from the original light. And when they drop down, they'll emit some light out. Of course, you know what amazing technological device I've just described? A glow-in-the-dark object. You shine light, you turn the light off, it continues to emit light, it's glow-in-the-dark. That's good. In fact, when you were a kid, it was awesome, but it's not a laser. To make a laser, there's two ways the electrons can drop down from the mezzanine. They can fall on their own, like a glow-in-the-dark, or they can be pushed. If I push them, that means that I'm sending in one photon of light, which triggers this one to go, which triggers this one to go, which triggers this one to go, to this one to go, this one to go. And at the speed of light, they all wind up dropping down at the same time. That means that I get a large burst of light. They're all coherent. They're all in phase with each other. They all have the same color, the same energy. And now I get a laser. Light amplified by the stimulated emission of radiation. Laser. When the laser was first developed, the public journalists said that scientists have developed the death ray. This is not a death ray. This is a death ray. No. But the laser does have a lot of applications. Ted Maiman built the first working laser in 1960. By 1964, German industrialists were coming up with novel, innovative uses for this device, particularly when they wanted to get rid of a British secret agent. 4 years from the invention of the laser to 007. But actually, the main application is storing information on these small, shiny disks, almost compact, you might say. When you look close up on these disks, you see a series of scratches or pits. And they are there to encode information. I'll shine a laser beam off the disk. If it hits one of the shiny spots, it'll bounce off and hit a sensor and get detected. And I'll call that a 0. Or if it hits one of the pits, it will bounce away from the sensor, and I'll see no light. So I'll call that a 1. And so by the location and the spacing of the pits, I can encode 1s and 0s. And the 1s and 0s can be used to encode information to send voltages to a speaker or some sort of other device. Because I can change the spacing between the orchestra and the balcony, I can change the color of the laser light. But back in the 1980s, it was difficult to make solid-state lasers that were inexpensive unless they gave off light in the infrared. Infrared light has a low energy and it has a long wavelength. Long wavelength means that the pits have to be spaced far apart so that the light doesn't overlap with them. So that means that there's only enough space on the CD to encode the information, say, for music. But by the 1990s, red light lasers that have a smaller wavelength were developed and became inexpensive enough. And now I can put the pits closer together so I can store enough information for both music and video. And so I can make these digital versatile discs, DVDs, could actually play a movie. And now we actually have inexpensive solid-state blue light lasers, which have a much smaller wavelength still. And so we can put even more pits so we can store even more energy, more information, so we can have high-def movies on a single disc. So thanks to quantum mechanics, we can replace 10 of these with 1 of these. So the Schrödinger trying to understand how atoms interact with light leads to MRIs, leads to DVDs, leads to the iPods and laptop computers. So this, I've talked long, but I'm a professor. But there's more information in the Physics of Superheroes, an amazing story of quantum mechanics. And so before I take questions, I want to leave you with one final message, one message from the ringmaster of the circus of crime. Please concentrate. Focus all your attention on the next slide. Thank you all very much.
So we have time for a few questions. Raise your hand. I think there are mics around, and I'll pass over. Choose your victim.
Okay. Yes, go ahead.
With new superconductors coming out, what challenges would you set graphene man?
Okay, graphene. Okay, so the question was with new superconductors. Did you say super or did you mean semiconductors?
No.
Okay, okay. There's like graphene man. There is a, stop saving. So what is graphene? I think I might actually even have this. Let's see. I got a ton of extra slides. Yeah, you guys are lucky you're not getting the full job. I don't think I have it here. Well, I can show you what this is, at least. This is actually, well, this is graphite. Graphite is pencil lead. And it's carbon atoms arranged in a hexagonal pattern. So every carbon atom is bonded to 3 other carbon atoms. But carbon likes to form 4 bonds. So one bond is below, and one bond is above. So it's kind of weak because it's only half bonded to the layers of top and above and below. So you have these layers of carbon in this hexagonal pattern in graphite. And they're stacked like, the layers of crust in a baklava pastry, like in phyllo dough. And they're easy to push apart and pull apart. So you can easily, so when you push with the pencil lead, you're actually unpeeling the crystal layers by layers. And depending on how hard or soft you push, you either pull a little or a lot of the layers. If you had a layer 1 atom thick, that's so special that it's called a special name, not graphite, but graphene. And because the electrons have nothing moving through the top, they can be either above and below. There's a quantum mechanical amazing trick that they can travel practically at the speed of light as they move along the surface. So people are thinking transistors. They're thinking all sorts of high-speed electronics. The Nobel Prize for physics was awarded to Andrei Geim and Viktor Novoselov in 2010 for making graphene, excuse me. And they did it in a very sophisticated way. They took some graphite, some pencil lead, and they took some cellophane tape, and they put it on and they peeled it off. Then they put some more tape and they peeled that off. Then they put some more tape and peeled that off. And eventually they got a layer that was only 1 atom thick. And then they did measurements on that. So go home, and if you have a pencil and some cellophane tape, you have all the tools you need to do Nobel Prize quality research. No more excuses. And so what comes out of this could be high-speed electronics, but the problem is that their sample was microscopic. What we'd love to be able to do, which no one knows how to do yet, is make this in large areas, mass production, and can you do it cheap, right? So that people are working very hard on. There are all sorts of fascinating properties of this material. If you take it and you can roll it into a cylinder, you would have a cylinder that's only 3 atoms in diameter. It's 1 atom thick on the surface. It's made out of carbon, so I call that a carbon nanotube. These are one of the strongest materials in the universe. If I could take a carbon nanotube and braid enough of them to make a fiber, a cable, like twirling the cable, that is no bigger than the period at the end of a sentence in my book, that cable could hold up 2 SUVs, 2 trucks, right? That cable alone, that you could not be able to see with the, you could barely see because it would be the size of a period. That's how strong this material is. So again, we would dearly love to be able to mass produce this, but we don't know how yet. So a lot of the interesting challenges that remain are engineering and material science, which are really hard. The physicists have the easy job. We discovered this new thing. Okay, we're done. Great. Hey, we made it possible. Making it possible and making it is two very different things. So it's the engineers that in many cases are the true superheroes. You saw the technology to make a Blu-ray, the physics of it existed a long time ago. It's getting those lasers to be cost effective, figuring out how to make them, mass produce them. That's the trick. So the engineering is just as important. What was it? I think it was Petrovsky who said, science answers questions, engineering solves problems. And you need both. Right? You can't solve the problem without the answer, but having the answer alone doesn't necessarily get you home. Any other questions? Way in the back. Oh.
This will be the last one, I think.
That'll be the last one? Okay.
Maybe one very short one after.
Okay.
Okay, it's a short question. I'm just reading your book at the minute about quantum mechanics. I wanted to know which of the aspects of quantum physics was the most hard to describe in layman's terms.
The whole notion, the question was, what was the hardest part to describe in layman's terms? And I think this whole notion of a wave function. So quantum mechanics says that there is a wave. This I can find easily because I already used it. Here. This is the Schrodinger equation that I told you. And this basically, he got to it through conservation of energy. But another way of thinking about it is that it's a kind of like the form of, it's the quantum analog of force equals mass times acceleration, F equals ma. You tell me the forces acting on the electron that enter through this term v, and I'll get the wave function that can tell you where the electron is at any point in space and time. Schrodinger misinterpreted his own equation. He thought that psi, when you squared it, gave you the charge density. And it was another physicist, Max Born, that said, no, it's the probability density. And the whole thing with Schrodinger's cat, that I don't have time to go into right now, was proposed by Schrodinger to point out how dumb he thought that idea was. How much he opposed this probabilistic interpretation. But the notion that there's a function that contains all the information about where the electron is going to be at some point in space and time, but only after you square that function, multiply it by itself, so that this is the most important function for the electron, this psi, but it itself cannot be directly measured, and it has no physical significance, no physical reality. That's why I said, oh yeah, light has photons and there's matter wave, because I focused on what I called a working man's interpretation of quantum mechanics. Because one of the most amazing things about quantum mechanics, yes, it's very confusing. I think it's even more amazing that you can use it correctly and successfully, even though you're confused by it. Schrodinger was 1926. We are still arguing over the interpretation of this equation. And yet, the transistors work, the lasers light, right? The MRI works. So, we can use this. The engineers can use this. We can design devices. They can function as planned, as designed, even though at the root of it, we don't understand what's going on with the electrons. That's one of the most difficult things to explain to a layperson, because I can't explain it to myself. There's people talk about the Copenhagen interpretation, or the this interpretation, or that interpretation. Actually, people joke about it, but there's an interpretation that I subscribe to, which is the shut up and calculate interpretation. It's like, what is it doing? Shut up. Just do it. When I need the electron to be a wave, it'll be a wave. When I need it to be a particle, it'll be a particle. It bothers me that there's no better justification than that, but it works, which in some sense bothers me even more.
Unfortunately, we have to stop there, but we will be moving through to the signing tent next door. Please do follow us. Give us 30 seconds to take a seat and then come with all your questions
Right.
and join us.
Thank you
you all
very
so much. You've been a fantastic audience. A huge thank you to James Kakalios.
We've been to see an event by James Kakalios on quantum mechanics, on his books about quantum physics and superheroes, and about how they tie in quite nicely.
I have a background in comics. I'm a big comic book geek.
I have a background in science. I'm a big science geek.
I'm a massive Batman fan. I've got my Batman watch on at all times. I quite like Punisher. I like loads of different stuff. Mostly DC, although this was more Marvel based. I think it was still quite a good event. I got a lot out of it.
Well, I did science at university. I did pretend science, environmental science at university, but since then I've been really interested in quantum physics, and this is basically exactly what I wanted to see from a book festival. It was amazing, it really was.
Yeah, we really like the book festival because you get to see authors, you get to actually meet the people behind the books, and it changes your perspective on what you've read, because you can hear their voice when you read a book again, and you can get their sense of humour a bit more when you read something, and it's just a unique experience, I think.
Absolutely, and they can extrapolate on things that they've said in their books and give you more information and possibly clearer than they would in their books.
Yeah, we've just come out of talk with James, I can't pronounce it, Kakalios or something? Yeah. Basically, he wrote the Physics of Superheroes, and I didn't do science very well at school, so it's really interesting for me because I'm a huge film fan and a comic book fan through that, or graphic novel, should I say. So yeah, he actually made me understand some things that I probably couldn't tell you about right now, but once I read the book I'll know exactly what I learned.
We went in depth about quantum mechanics, something that I had never really understood beforehand, so yeah, it was very insightful. and he's absolutely hilarious.
Yeah, it's really funny.
So funny. I sort of collect Star Wars comic books more than anything, so I'm not sort of I'm into Marvel and DC, but not as much as Star Wars. I've got the original 1984 Return of the Jedi sort of collection of comic books. I know. So yeah, so this was sort of just an expansion of what sort of comic books and graphic novels I like and stuff. So
I think it's awesome. Obviously as the films are going out, like your Iron Man and everything, it's getting more popular for everybody. Yeah. And I think geeks are kind of coming out the closet now.
It's sort of cool.
It's more acceptable.
It's cool to be a nerd now, which is nice.
I think with Big Bang Theory and everything, and people are going about with the t-shirts seeing geek and nerd, and so I think the event's going to be more popular than it might have been a few years ago because of it.
And I think it's amazing that they're doing an event like this, especially at the International Book Festival, where it's sort of in the past it's been sort of literature driven. It's really nice to know that they've got a sort of they're outreaching and stuff. So it's really good.
We love the Book Festival.
I'm a little bit obsessed with books and writing. I try and do some writing, and it's just a really great atmosphere and venue. It's multi-purpose, it's good for kids and people of all ages. There's food and booze if you need it, there's a bookshop, there's interesting people, you can chill out, there's chairs and benches, and I don't know, free mini Spiegel tents, and it's fantastic. See, look, I really like the book festival. So I don't know, it's a combination of things. Yeah. You learn something, you meet people, random people in queues. I met Adam Marek, this author I met in the queue for Chris Ware the other day, and he's really interesting, nice guy, and I'm going to read his book, and just stuff like that, you know. There's a good bunch of people around, it's a good vibe, chilled out. It's like a little oasis of calm and tranquility as well, but also there's a buzz. It's like the best of, I guess maybe not both worlds, many worlds, the multiverse.
The event was quite amazing. He was the most fantastic lecturer who just brought the whole thing to life. My father was a science teacher, long since dead, but this is the sort of thing he would have loved. He taught in the age of radio vowels and then was amazed by transistors. He'd have enjoyed every moment of this. It was great.